let me. Okay. So we have like kind of another like string problem again, but this time it's a little bit complicated. So this time we have a string of n lowercase letters, n less than 10 to the fifth. So be careful about this. We can't do anything n times like n squared or anything else doesn't work, right? And we have a string. Oh wait, I forgot. Oh, I'm annotating again. Oops. Okay, so we have n less than 10 to the fifth, right? That's pretty big. And we want to once again, I think this was came up again this year, but we want to like count like we want to kind of look at the occurrences of moos. And a moo is basically a three characters that have the pattern x, y, y. I'll just call it that, where x is not equal to y and they fall in this order, right? So like they gave like an actual like, straight up like thorough description here, but I hope this is like clear enough to everyone. So we can just have like x dot 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 y dot 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 y with x. Yeah, so they have to be in this order. X not equal to y equals y, obviously. Okay. Now we have a now we want to for every single moo like this, every single triplet, we have a we are given a formula to calculate its value. Basically, we take this string, right? So let's say we take this string and then we bend it at this number so it turns into this dot 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 y dot 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 y. And then we calculate the area of this triangle that it forms. And in more like mathematical terms, all we're saying is that, okay, if this is at index I, this is at index j, this is at index k, right? We're clearly doing j minus I right here times k minus j. Divide by 2, but I think I didn't really care. Okay. Yeah, so we were just looking for this query. Now we're given a bunch of queries and Q queries. Q is also pretty large, less than 3 times 10 to the fourth. And in each query, we're given two numbers, L and R. And we want the maximum value among triplets I, J, K, such that like the triplet is strictly in between this range, and we're trying to get the maximum value. Or if it doesn't exist, we output -1. Okay, so there's a lot of parts to unpack about this problem. Like a lot. So let's try to work through this step by step. When you see a problem like this, first of all, let's see. Okay, so the answer is talking about maximizing value, right? Right. So first, let's see how we do this. So, well, you can either occur this, but or you can actually I'll talk about the brute force later. I'll talk about the main solution for now. So if we want to maximize value, mm, actually, do I want to? Actually, no. I'll talk about brute force first because I think the brute force is kind of they kind of give a hint as to how to do this. Okay. First brute force case. NQ less than 50. Well, these numbers are really small, right? And I hope everyone can kind of have an idea of how to do like the most straightforward kind of a solution. I think the most straightforward solution is just, for every single query, right? For every Q, loop over all possible triplets. Okay, so this is pretty straightforward, right? So we have an L and R, right? We loop over I, J, K within it. So if you do calculate this, right, each one of these can theoretically have n things to be, so that's n cubed, right? And then once we have a fixed I, J, and K, right, we just have to make sure that, A of J equals A of K, not equal to A of I, right? This satisfies a condition. And then if this condition is satisfied, that means it's a valid like moo triplet, right? And then we just have to compare the formula we use to get the value. We have to compare this to the best answer we found so far, and we just output the max of this. So it's n cubed per query. So that means the overall time complexity is O of Q times n cubed. And for n equals 50, the nq less than 50, that works, right? That's the most straightforward solution. So obviously this is not going to work for anything above this test case, but now let's look at the second test case. So second test case is q equals 1, and the query satisfies L equals 1, R equals n. Okay, so this is already starting to give us a little bit of a hint as to how to do this whole thing. So this is what this is saying is that, okay, we given a number, what's it called again? We're basically given 1 and n. Oh, or we just want to find the largest value the triplet can have in the entire array. Okay. And hopefully I think if you've observed, if you've done the last few USACO bronze contests, right? And you had like, I think we've had similar problems this, right? The solution every single time is basically, instead of looping on the fact of like O of n, right? Instead of looping over the whole array, instead let's loop over every single distinct character, right? Observing the beginning, right? The A string of length n consists of only lowercase alphabetic characters. So there's only 26 unique characters in there, right? So that means that if we have what's it called again? If we want to make like moo triplets of the form like x, y, y, there's not that many total like different. Oh, there's a lot of different numbers we can choose, right? Up to n cubed. But if we only care about like the letters involved, right? So like some letter A, some letter X, some letter Y, and like so these are like variables representing like letters, right? There's 26 options for X, 25 options for Y. So we just call it 26 squared, but either way, it's like on the scale of like 600, right? There's not that many total ways to write X, Y, Y. But the issue is for each one, like let's say we fix X, Y, Y to be like A, B, B, right? Let's say we fix it to be this. There could theoretically be a lot of different ways to compute it, right? Let's say our array initially is like, this. Okay, right? There's a lot of different ways we can choose an ABB. Like once if we fix like, oh, we have to we're trying to look for ABB. There's a lot of different ways to do it, right? We could choose this A, this B, this B, this A, this B, this B, this A. There's so many ways, right? We see that the number of ways to choose this is on the order of A cubed. So that's not really going to work. But it would work if we're able to find a good way to like say, okay, if we say we want an ABB, right? Then we want we want to find a way to like maximize the value of like this value of this a triplet with this form. So pretty clearly we can already see that, if we're allowed to use the whole array, the optimal spot to pick A is just the first one, right? Like even if there's not a B before, right? We want to pick the first occurrence of A. Because this like, you know, if we look at like how the formula is calculated, right? It's kind of based on the whole length of it. Right. So there's no advantage to picking like an A that's farther back, right? So if we pick like this A instead, no matter what B's we pick, let's say we pick this B and this B, right? No matter what B's we pick, it's gonna be like a shorter distance here than if we check this whole distance. So I think this fact is pretty obvious. So A should be first occurrence. And okay, so this I hope this fact is pretty obvious. So yeah, there's no reason to ever pick a farther occurrence of A than the first one. So let's say we just, fix this one. Now we want to fix B. Likewise, same for here, right? If we pick this B instead of let me erase the other ones, right? If we pick this B instead of this B, then it doesn't matter where we pick the second B, right? We make the second B here. Evidently, we're getting a shorter distance from this to this from than this to this. Correct? So B should be the last occurrence of that letter. So like it doesn't matter if there's another A back here, but it's like because we're not picking A as the first number. Right. So this should so this should be also so these two are both fixed. Now we want to pick what number we want in the middle. So far we fixed this A We fixed this b, and now we want to find another b somewhere in the middle. Now, if you know anything about geometry, I think okay, the actual proof of this is like is calculus because it's optimization. But I think if you've done some geometry, you should have some intuition that like if I have like okay, if I have like the sides of a square, right? Let's say the sides of a square have to add up to like a certain constant, right? A constant c. Yeah, constant c, right? The optimal sides, well, like not square. So like if I have a rectangle and I know the sides have to add up to c, which is some constant c. The best way to pick its two sides are going to be c over 2 and c over 2, basically making a square. Now, yeah, the proof of this is calculus because you're optimizing something, taking derivative, but like you don't need to know this. I think this fact is also kind of obvious, right? Because if I have like one straight line, right, the best way to bend it to maximize area is just in the middle. Because if I bend it anywhere else, right, let's say I bend it close to the end, I'm barely getting any area out of this. Like this is like if I bend at the end, I'm getting like this. If I bend in the middle, I'm getting this huge square. So the square is always the best way to like optimize for area if I have a fixed perimeter. This is kind of a yeah, this is just kind of a geometric fact. Right. And in contest, I hope you could have like, prove this to yourself with like some examples. Like not prove, but like convince yourself of this fact, right? Like a square is better for area than like a long skinny rectangle because, if you have the same perimeter, this skinny rectangle is barely contributing any area. So, but basically what we're getting from this is that if we have like a fixed perimeter, or like fixed half for perimeter, then the best way to allocate side lengths to get area to maximize area is splitting it halfway. So 1, 2, split halfway. So does anyone have any questions about this part, by the way? I think this is probably the most important. Well, actually, I won't say the most important, but like yeah, this is like a really crucial observation you have to make. Basically, if we fix the endpoint, the start and the end, the place we want to put to choose the second number, no, the second character is in the middle. That's optimal. Okay. And yeah, so second, yeah. So second B should be halfway. And so far I haven't gone into at all how to implement any of these. So now I'll start getting into it. So we have to find a way to implement this in pretty quick time. So okay, for this question, for this query, these three facts is all we need, right? This is a pretty way to implement it. Even though so there might not be an there might not be a b at the exact halfway points, right? But we just want the b that's closest to the halfway point because like we can see, right? Like a rectangle that's like is slightly more square shaped is going to have more area than a rectangle that's like slightly less square shaped, right? Like this rectangle, even though it's not a square, it still has more area than this one because it's more square shaped. So we want to get it to as close as possible being square shaped, right? So yeah, for this test case, this is enough. We can loop through to find. So we basically first do the 26 times 25 ways to find ABB. So ABB is just like, so it doesn't have to be ABB, obviously, right? It could be CDD, CAA, whatever. Any of these pairs. But that's like 600, right? And then for any of these, we can basically loop through, find the first occurrence, O of n time, right? This is O of n. Find the last occurrence, O of n time. Find the halfway point, O of n time, right? Because we start from the middle and just kind of like look out from both sides and try to find the first one that's closest to the halfway point. And so overall, the time complexity is 26. I'll just call 26 squared. It's slightly greater. 26 squared times n. And for n is equal to 10 to the 5th, this comes to around like 6 times 10 to the 7th, which works, which passes 9. Okay, so Any questions about this part, about this test case? Yes, no, maybe so. No. Okay. So if not, then I'll go on to the last test case. The last test case is actually pretty hard. Since I have time, I'll go over two different ways to do this. So far we know, so for each query, we can do in O of n time. Well, not strictly O of n. It can do in O of 26 squared times n time, right? And this doesn't actually pass for q is greater than 1, right? Because obviously n is 10 to the fifth, q is 10 to the fourth, nq is already too big. Add this constant and it's like way too big, right? So this will never pass. But we can do some things to try to reduce this down. So obviously the queue can't shrink. So we need to find some way to solve each query in a pretty quick amount of time. So let's go back to what we're actually looking for. So what we need is finding the first occurrence, finding the last occurrence, and basically splitting it halfway. But actually, yeah, okay, yeah. So same thing. Yeah. Um, let's see if we can do this in less than O of n time, basically. So consider storing every single occurrence of every single number of every single character into either a set or a vector. It doesn't matter. But if we store it in a vector, basically we store the positions of every single. So we have let's do a vector. Let's do a set. Let's do a set. So set of S, right, of 26. So what this does is this set stores for every single character from A to Z, every single index it appears in. So for this array, right, it'll be like S of 0, which stores A, will store like 0, 4, it should be probably 3, 4, 5, and then the last character, whatever it is. I don't know, forgot what the last one is. Don't account. And then S of 1, which stores B, will store 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? This stores the index, so I guess this one was 12. So basically, an S of like 3, 2, 3, everything else is just blank. There's nothing there, right? Because there's no other occurrences. But basically, what this set is doing, right, is storing the indexes of every single occurrence of the characters. Right. And wait a second. Okay. So we're storing the indexes of the occurrences of every single one of these characters. And using this, right, we can pretty easily find the first occurrence within a range. So yeah, for the general case, we also what we've done in this case, right, it was actually even easier because we knew that the range was from 1 to n. Now the range is from L to R, but this doesn't change much, right? We just have to find the first occurrences within this range, last occurrence within this range, and split the halfway, right? Same thing. So it doesn't change too much. But now we can do a pretty easy query on finding the first occurrence within this range of a letter A by using the set, right? And how we do this is basically binary search, but we don't actually have to code out binary search ourselves because std set has something stuff built in, right? So we can do std set. I think probably lower bound for this one because. And so what this does is it finds the first element, which is not considered to go before the value. So basically, its equivalent goes after. Basically, it finds the first value that goes after the value that is equal or after the value you're looking for. And this is exactly perfect for what we're doing, right? Because like let's say for this case, we want to find, let's say L equal to 3 or L equal 4, let's say. Right. So if we do a lower bound search on this set, we just get 4 because we see here that there is an occurrence of A that's greater than or equal to 4, and this is this occurrence, right? This corresponds to this one. right? And similarly for the for this, so this can be done, and this is binary search on a set, so this is log n time. Similarly for this one, for if we want to find the last occurrence of B, pretty easy to do. Same thing, we use set lower bound, but instead of lower bound this time, we probably should use upper bound because we want to set upper bound. It doesn't matter. Like just find some way to implement it. But basically, the best way to do this, right, is we can just do upper bound on r+1. So we find actually no, lower bound, probably lower bound. Lower bound on r+1. So we find the first occurrence that is considered to go after r, and then we go backwards one from it. So it should be upper bound, lower bound. Lower bound of r+1, and then subtract 1. And this gives us the correct index of the second one, the last occurrence of B. Right, because like, so let's say for this case, right, r equals, let's say, I don't know, 9, right? So what we're doing is we do lower bound than r+1, so we get this one, and then we go backwards one, so we get 9 exactly. And this is correct, right? Because we can, you know, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this will correspond to this one, right? So L is here, R is here, and we found the first instance of A, the last instance of B within this range. So this works. So now the hard one is we want to split it halfway, right? So how do we do this? So we want to find the one halfway. So let's say, currently L equals 4, R equals 9. Halfway of this, midpoint is equal to 6.5. Let's round down to 6. Okay. The issue here is that we don't necessarily know, like, if there's nothing exactly on this midpoint, right? We don't know if the closest occurrence comes before or after, right? So let's say like midpoint is here, right? There might be an occurrence here. There might be an occurrence like here, right? Here, clearly, right? This one is closer to the midpoint. But since neither of these are exactly on the pinpoint, we don't know which one to take. But we can actually get around this pretty easily by basically, okay, we query for the midpoint, and we know that this midpoint is like slightly below. We query for this one, and we check the ones before and after. And we just want to see which ones are closer. So, yeah, so like we can just do a lower bound search on this. Lower bound. Lower bound will find the first number, or we can just do upper bound. Let's do upper bound. Upper bound on this. It doesn't matter. Like just basically another binary search on the occurrence that is closest to this, right? And then we check before and after this. And the time complexity of this is also, so for this case, right, we'll search for this, find 6, and we can check 2 and 7. And we basically take the values that are within this range and give us the best results. So for this case, I think 6 and 7 give the exact same results, so it doesn't really matter. But yeah, you have to check both sides because you're not sure which one exactly closer. And the time complexity of this is also log n because all the time complexity mainly just comes from this upper bound function or lower bound function, whatever. Both these are just binary searches. So now we've gotten all 3 of these time complexities down to log of n instead of O of n, right? And that's a lot better. So now our overall time complexity is O of 26 squared times Q times 26 squared. Q times 26 squared times log n. Now, if you manage, I'm not sure if this passes if you manage to get it down low enough. I think we tried coding it and it didn't. So this actually, but theoretically, maybe with enough optimizations, you can manage to get the solution to pass. But it'd be very close. It'd be very tight. So I don't think this is the intended solution. The intended solution, we can actually drop another 26. So with a little bit of optimization, we can actually drop another. So we have to optimize this even further. Yeah, because if you calculate the time complexity of this out, this is going to be 3 times 10 to the 4th times 26 squared times log of n in this case is close to 20. Let's just say 18. Right, and you're getting 3 times 10 to the 8th, which is suspect. That's like 3 seconds around. So pretty hard for this to pass. Right. This is pretty tough to pass, but we can actually lower this even more. How do we lower this more? Well, so far right now we're looping over every single possible occurrence of like X, Y, Y, right? So ABB, AB, ADCC, ADD all the way on, and then BAA, BCC all the way on, right? Okay, but this isn't actually optimal because like let's say we have a range, right? Let's say we have a range from L to R. And I'm gonna start using other letters now, not just A and B. Okay. So pretty clearly, right? If we're not using pretty clearly, because we say that like so A should be the first occurrence, right? Pretty clearly, we probably should just take L as the like as the first letter. So unless we're using like right, because for any if we're matching up this number or this letter A in this example, right? But if we're matching up this letter with any other letters here, right? This is going to be the optimal number letter to choose, right? So let's say we pick these two numbers as our YY, right? So if our in our XYY triplet, right? Let's say we pick these two to be our YY. There's no reason we should pick like this number, this letter, any of these letters except for this one. Correct? Like because this is going to be the one that optimizes area for these two Ys. So pretty clearly we should just fix our like XYY X to be this letter A. And then we loop over the other 25 letters to try to find our YY. Right. And we can do this, we can loop over the other 25 letters the same way. So we do the log n solution, right? Last occurrence and midway, right? That's all the same. But now because we fixed the first letter, instead of doing anything else, we're down to 26 times n. Correct? But this actually misses out on one case where maybe it's optimal to use this like A eval. I'll denote like this actual letter as A eval, right? Maybe it's optimal to use this A eval as Y instead of a X, right? Because like so far we're ignoring the case where A eval was being set to Y because we're saying that okay, we're setting A eval as X and we ignore everything else. And then when we're doing Y, we basically ignore having A eval because we can't do like three letters as we can't do AAA. That's not a Moo combo, right? So there's actually only one other case, and that's basically saying it's A of L, first case, right? A of L equals X. Or X equals A of L. So X equals A. There's actually only one other case, which is that Y equals A of L. So this is the one case we're missing. And if we have Y fixes A of L, we can just loop over other letters for X. And this way we do basically the opposite, right? We find we have X, we have Y fixed, we loop over X, and each time we still do the same queries, which is still log n. So the time complexity of this is also 26 times n. So the overall time complexity now for each query is 26 times n plus 26 times n. No, it's plus now, right? So it's basically a constant factor. So we can just write it as Q O of Q times 26 times n. Well, times log n. Well, no, not times n, times log n. Should be times log n. Times n is huge. Times log n. And this passes because, if we go back to our calculation, if we remove a square from this, this is like, 1 times 10 to the 8th. Oh, no, 1 times 10 to the 7th. So this is like, this very clearly passes. And this should be the intended solution. Are there any questions about this? I know this was kind of a lot. How do you calculate how long it would take? Basically, I'm calculating like there's a lot of parts to it, right? So I mean, like like the query part for each one. So I can do these 3 queries. Each one of these is log n time because the most time inefficient, like the most like time intensive part of this was the query, the binary search, like the lower bound. So every single one of these is log n, right? So every single time if I have a fixed A and a fixed B, where like A and B are both like characters, if I fix A and B fix B, I can find the optimal one in log n time. So now the question just becomes, how do I minimize the number of pairs A, B do I have to query? And here we brought it down the number of pairs back to basically down to like 50 pairs because we can fix one of them, fix either X or we can fix either Y. So we fix X, there's 25 numbers, the other characters loop through. If we fix Y, there's another 25 characters loop through. In total, there's going to be 50 characters. So time complexity is going to be, I guess 26 is not super accurate. It's like O of Q times 50 times log n. But like, yeah, you kind of get the point. It's on the same range. It's like 2 times 10 to the 7, which will pass. Any other questions? N log n is the most for passing? No, no. N log n usually passes with also notice here that Q is actually smaller than normal. So a lot of times when they want the solution to be n log n, they set n to be 10 to the fifth, 2 times 10 to the fifth. Here, Q is 3 times 10 to the fourth. They do it because they want to allow like this 26. They want to allow this Q times 26 times n solution. Yeah. Like I think this is probably intended. There's actually there's another solution to this. It's basically the same thing. So here I'm basically fixing X or I'm fixing Y. I think this is the solution that requires a little more thinking. There's a second solution which basically is a little more pre-computation. So here we notice that basically same thing. It's either that it kind of has the same observation where like we basically should pick A or we should pick like the first number that isn't A if we want to use A as the second number, right? So we either use A or we find the second, like the first number that is not A. And the issue with finding the first number that's not A is like, let's say our range is like A, and then like C, right? If we want to find the first number that's not equal to A of L in this range, if we don't do any pre-computation, we have to like loop through everything, right? And this could theoretically be O of n if like the array is like pretty much the same except for one thing. But yeah, we basically so you have to pre-compute this. And the pre-computation is like it's not that bad. You basically for every single range, no, not every yeah. No, for every single starting point, you basically make an array like pre-compute, pre-comp, and then like let's say it's basically saying for every single number, the first and second number, like the first and second number, you like the first occur you store like the index of the set of the first letter that's not equal to like this letter, basically the letter where it starts at. It's kind of convoluted, but so this is why I didn't really like it. But if you think about it, it makes sense, right? So like pre-comp I is just like equals first index of first letter that's greater than I, but that's not equal to A of I. And we could just use this as well. So that way we don't have to fix Y. We can just like X equals A of L first, and then first case, X equals A of L. Second case, X equals pre-comp of L. Yeah, and then we can keep going from there. But that's a lot more. Yeah. X equals L case. But why is at Y equals L in other case? Because the issue is if we only consider the X equals L case, then we're basically ignoring the Y equals L case, right? Because if we fix X equals L, then we're just saying that Y cannot be equal to well, A of L. But we're saying that Y cannot be equal to A of L, right? But maybe the optimal answer needs Y to be A of L. So we have to consider that as the case. Do you know what I mean? Like the second case is like X equals like something else, and then Y is equal to A of L. That's the second case. Does that kind of make sense, David? It's issues like this case works for everything except for the edge case where the optimal answer has Y be Y. Yeah, okay. So it's basically just accounting for an edge case. Okay. With that being said, I think that's all the time we have. Yeah, this one was pretty complicated, but I think honestly, I think this contest, in my opinion, I think this contest was. Let me screenshot the slides again. I think this contest was easier than the previous two, like honestly, because I think 1 and 2 on this contest were pretty easy. Uh, We didn't write the XCAM courses, but it's probably like just like the XCAM course is probably just 200. Like for actual like knowledge you need, it's most of the knowledge you can be getting from probably XCamp 201, 202. They'll teach you like how to use like STD set and stuff like that. And that's theoretically all the knowledge you need for all this. But what you do need is just a lot more practice. Like I think one and two was very easily solvable. I think the cutoff's probably going to be like 700 plus because one, two, and then like B3, you could have gotten the first two subcases. Second one's a little harder, but I think the first subcase for B3 was pretty free, and that probably gives you above 700 already. 852, yeah, 852 is 100% enough. So wait, is 832 just like solve one, solve two, solve three's first two subcases? Is that how he did it? Yeah. Okay. Yeah. 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 Like I think solve one, solve two, solve half of three was definitely possible. 832 is 100% enough. But like so I think the cutoff's probably gonna be 700 if I had to guess, but I'm not too sure. But yeah, I think solve the other half of B3 requires like either a good amount of thinking or like kind of like ability to like pre-compute stuff and like think stuff out on paper, which is yeah, like B3 was definitely very hard for bronze from, but I think half of B3 was definitely doable. And if not half of B3, definitely the first subtask could B3. So I think that should be your goal. And like B1 and B2 are really easy. Like they're like really easy this time. So yeah, I think just for future, if you just want, just practice more, obviously. Like every single one of these problems is like some kind of ad hoc problem, requires some kind of observation. And the quicker you can make the observation, the quicker you can, be able to start coding and solve the problems.